Piccadilly Circus, area 1970. Okay, as I recall, this was the last slide that I discussed last time, and I don't think I can use my pen in this room. I think this is one of the. I think this is one of the rooms that. Yeah. Pen. No, it does not like. Does not like this room here hardly. This pen's about right. I can't complain. I got about 3 years out of this laptop and it's still working, but its batteries aren't working very well. The pen's starting to die. Yeah, see. Oh, now it's going down. Before it was going up. Yeah, because here. Yeah, now it's going down. All right, well, regardless. Okay. That there. The last thing I talked about is that this was a question that I would consider open game for the final exam, and I wanted to kind of mention it again, is that these are the typical knowledge base for design and operation robotic systems. This is not an all-inclusive list, but it's one that it's a pretty good start if I ask you what, what technologies are involved in designing and building robots. If you gave me this list, that would give you full credit on a final exam question. There are other answers that fall into this but they're system modeling, of course. In other words, you have to be able to look at a system as an entire entity. And I don't care whether it's a robotic car or an industrial robot or a humanoid robot. You have to be able to model the system and analyze it. Feedback control is not used in all robotic systems, but most. And I don't know if I can repeat the concept of feedback control, but feedback control basically means that you look at the output of the robot's actuators and see whether or not it's actually doing the job it's supposed to. Now, is feedback control a prerequisite or a co-requisite for this course, or has everybody not had feedback control systems? Yeah. So in other words, some of you have not taken it yet. Okay. Well, I won't have any questions on the final exam about feedback control systems, but let me just take a moment here to, well, maybe. Bring up OneNote, if my pen works right there. Talk about feedback control. Here's OneNote. Right there. Okay. New page, all right. Basically, feedback control is you have, and I don't know how well my drawing is going to work here. It's probably not any worse than it is before, but you have some type of system right here. Right there. You have a known, a desired output. I'm just going to call it DO. There's better that there. I have a summing amplifier of some type here, where there's my desired. And we take and we measure the output, and quite often we put in some type of signal conditioning on the output in order to feed it back into our plus minus right there. And this is often referred to as the air signal, ET, right there. So, right there. And this is a feedback control system. And feedback control basically means that we're monitoring the output, we're comparing it to what we want the input, what we want the output to be. So, an example of a feedback control system that's relatively primitive is the AC in my living room at home. Now, these ACs don't have feedback. You either turn them on or off. There, you set the speed. So the feedback operation that there is this young lady here, if the room gets too cold, she walks over and turns off the air con. If the room starts to get too hot, you turn the air con up. So you're the feedback loop in this particular case. That's there. And, you know, these gentlemen can't do it because they're on that side of the room, and that's there. That's there. But regardless, for example, if you have a cruise control in an automobile, that they're not popular in Malaysia, at least not in the low-cost Perduas that I buy, that's there. But if you buy, say, for example, a Toyota or a German-made car, a BMW, they have what's called cruise control, where you can go down the highway, push a button, say I want to go a certain speed, and keep the car at this speed, right there. Quite honestly, it would be almost a waste to put one in a car in Malaysia because you can't go very far on a consistent speed. But believe me, driving from Indiana to California, where I've had to drive across the deserts of Texas, northern Texas, the Panhandle of Texas, New Mexico, Arizona, and Western California, where you can go probably 200, 250 miles and not see a tree, and the road is perfectly straight. Cruise control is kind of a nice thing to have right there. But regardless, the cruise control, the way that it works, and I'm just going to kind of give this as an example of a feedback control system, is that the desired speed is the speed of the vehicle when I hit the button right there. And typically the way that that works is that it's measuring the speed coming from a sensor on either the transmission, usually it's on the transmission, but it can be elsewhere in the car, right there. And it goes through some processing right there, and it goes to this air right there. So whatever speed is on the car at that time, that goes into my feedback, is my desired. And it's a capacitor that just holds a charge with an op amp so it doesn't bleed down right there. The system in this particular case is very complex. It's the automobile itself. It's the fuel injectors, the fuel pump that controls how much fuel that goes into the fuel injectors. It's the engine, it's the transmission. Those all control the speed of your car. You can't, I'm going back to my example of driving across New Mexico, for example. They have these little things as you go through New Mexico called the Rocky Mountains. They're quite steep, and then you go up them and you go down them right there. So you can't just keep the same fuel level going to that. You have to monitor the speed, because as you're going up the mountain, you have to increase the amount of fuel going to the engine. You may have to downshift the transmission in order to keep the speed consistent. When you're going down the hill, you have to reduce the amount of fuel going to the engine, and you may again have to downshift the transmission in order to keep the car from going too fast. Right there. So, but this is a feedback control system. You have an entire course on that, and I'm not going to teach that course in the next 10 minutes, but I just want to give you a kind of an overview of what's meant by a feedback control system right there. Right there, yeah, current slide. Right there. So we have our feedback. We will be spending some time talking about different types of sensors, and the sensors will show up on the final exam right there. And signal conditioning, I'm not going to dwell on signal conditioning too much here, because the types of signal conditioning you have are typically analog op-amp circuits, and you should have had a course in electronics, amplifiers and filters and those types of things. But that's what's meant by signal conditioning. You filter out, high frequency noise, You may filter out low frequency noise that's there. You may have to amplify the signal. You may have to do many different things to it right there. So, you know, a sensor is something that is able to measure a physical quantity and convert it to an electrical quantity in some form. There are thousands of different types of sensors out there. We're only going to touch a few of them right there. I've worked on everything from sensors that measure the amount of alcohol is in a person's breath, right there, for a breathalyzer. Right there. I've worked with sensors that look at the color of a potato, look at the color of a tomato, look at the shape of a tomato to make sure it looks like a tomato and not a rock. That's there. You know, when you're canning tomatoes, you probably want to avoid putting rocks in the can. That's there. So, you know, but sensors do all kinds of things. The most common sensors in robotics typically are proximity sensors, see if something's close, a distance measurement, how far you are from something, maybe how much light there is in a room. That there, you might need to know something like that. Cameras are a type of sensors. Actually, a camera has many, many sensors typically on a camera. So, actuators, those are motors and pumps and things like that, valves. Those are various things that can make something happen right there. So, power electronics. If your robotic arm has to be able to pick up the block of an engine, you can't use the 5 volts coming out of a microprocessor to do that. You need to bump that up with some power electronics out there. So again, these are all part of the knowledge base, you know, things that you need to do. Hardware and computer interfacing, that's a huge part of robotics right there. You have to be able to interface these various sensors to the microprocessor, to the microcontroller. You have to also be able to interface to the actuators and power electronics. So a lot of the computer hardware out there. And again, that's been my major area right there. And then the last one on this list is computer programming. Now, I'm not going to argue with these slides because these slides are very valid if you're designing robotics at the lowest level. If I'm working at Tesla and I'm designing a generation of, you know, self-driving cars, or Uber, and you're coming up with self-driving cars, by all means, the people at the leading edge, you know, they're doing a lot of tweaking on the programming, on detecting various objects and what to do. You know, I was reading an interesting article that I can't remember which automobile manufacturer it is that's working in Australia to do, you know, self-driving cars. They ran into a very interesting problem that almost all animals are fairly predictable when they run out in front of a car in the way that they behave, and that the car can be programmed to react to that particular. Same thing with pedestrians that there, you know. But they discovered that the kangaroo acts very erratically, and it's driving their programmers crazy on how to avoid collisions with kangaroos. Because kangaroos seem to jump right into the path of where the car seems to think that they shouldn't. That's there. So, so again, you know, there's all kinds of challenges that computer programmers have to come up with. And that also goes back to this dynamic system modeling analysis. That's there, where, you know, in that particular situation, part of the system is that kangaroo in the middle of the road. You know, monkeys behave a certain way. You know, that might be a problem in Malaysia, but monkeys evidently are more predictable than kangaroos. That's there. So, you know, and sometimes this all falls apart when you're dealing with systems, when you put a human in a system and the human behaves differently than you expect them to do. You know, in my particular case, I had a stroke 4 months ago. My reaction times are slower and different than they were prior to the stroke. So when I tried, as a result, I wasn't allowed to get behind the wheel of a car for a number of months. That's there. So again, there. a person who consumes drugs or alcohol is a huge, huge, huge problem for system modelers, because they're not acting, you put a human in the loop and they're not behaving the way that you would expect a driver to behave. They're erratic, they're not sane at that point. That's it. Back in the aerospace industry, you put a pilot inside the cockpit of a jet aircraft, that's there, and he's gone 14 hours without sleep, he's not reacting the same. And that's called the human in the loop, that there. Whenever you put a human in the loop, right there, part of the system is a human, this system could be very unpredictable, right there. So as we look at robotic systems here, we're trying to come up with machines that emulate, in some cases, human behavior or replace humans in the job market. But quite often, a human operator is still part of the feedback loop, it's part of the system. So the robot-human interaction is a huge issue that you have to deal with. That's there. Last part of the slide I kind of ignored, that these are the various disciplines involved in terms of study. I'm more concerned with what's in the yellow. Those are the specific skills that's needed for robotic systems right there. Okay, now we're getting into a little bit more detail. I don't know how far we'll get into today's slides. Actually, I promised to carry the robot down, but I'm in no condition to carry that robot down. I think I'm going to wait till Tuesday or Monday and have someone else carry it down for me after we start talking about the robot. But right there, the power conversion unit, and I keep forgetting I can't draw on this thing, is what draws the power from the lab or the power panel at the factory, whatever. That's fairly basic. That's power electronics. There, no, we won't talk about that. That's usually a power pack if you're buying a commercial robot that's built into it right there. You have your various sensors right there. The sensors tell the robot where it's at in space. Normally, it tells the robot whether it's got something picked up or not picked up. It tells the robot whether or not there's a part on the conveyor belt or the assembly line for it to work with, right there. But those are the eyes and ears of the robot, right there. The eyes, ears, fingers, right there. Then you've got the controller. The controller is the heart of the robot, that's why it's the center, and it talks to pretty much everybody else in the robot system. The sensors don't talk directly to the actuator. The sensors don't talk directly to the user interface. The sensors only talk to the controller. The actuators talk to the controller. They also have to pull power from the power system. So if you've got a motor, for example, a DC motor, that there, and let's say it's using pulse width modulation, which we'll talk a little bit more detail about that, in order to drive the speed of the motor, that there. We have to be able to use the controller to control the speed, but the power has to come from the power source right there. And of course our actuators have to be tied to what it's going to move. In this particular case, they call it the manipulator linkage, but that's a fancy term for what you're moving, the arm, that's there, the hands, the grips. In other words, you have, in this particular this slide here, they don't differentiate between the end user, the gripper, for example, and the arm. And right now, I mentioned my particular situation. My gripper doesn't always talk to the controller. What happened to me is I had some damage to the brain, and what controls my actuators, which is my hands, my legs, and my arms on the right side, doesn't work all the time. So my problem is here in the controller, right there. My actuators work fine. My hand works perfectly fine, but every now and then my brain has a short circuit and says open, and I drop coffee pots. Fortunately I caught it, but I made a mess in the lounge just before I came down here. I had to clean up because my hand just kind of like go. Well, I mean, those are bad things when you're talking about real robots. And again, I'm not trying to highlight my physical problem, but how it ties into robotic systems, because the human being is a brain, is a computer system out there. It's a large neural network that does computer processing. Alice gave it the power to do that, and it's also very intelligent in comparison to robots, and does things, but it malfunctions right there. And same thing with our controllers. If it malfunctions, we don't want this robot arm swinging and knocking the operator halfway across the factory floor either. So we have to accommodate for what happens when things go wrong right there. So, but this particular slide doesn't separate from the gripper and the arm right there. So right now my wife is having trouble with her arm, and she's had shoulder surgery, so she can't move her arm right now. So in that particular case, we're a lovely couple. We have one pair of arms between us right there. She's got a good right arm, and I've got a good left arm. So that's it. But here, and I can't draw, we also have the base. The base is what our robot is mounted to. Yeah, I don't know. Oh, this thing is. Oh, this is the problem. Okay. Right there. Again, I gotta make sure I don't bump that. It's not all robots are mounted to a base. You saw the video, or hopefully you've seen parts of the video, of the ones that are on wheels, the ones that are attempting to walk. In that particular case, the base is the floor where it's trying to move across. Most industrial robots are mounted on some type of base. So, and then the last one that I haven't talked to is the user interface. Now, the user interface, if you're talking an industrial robot, is usually a programming module. Something you go out on the factory floor and you walk it through the steps and tell it what to do. You show it what to pick up, and you give it the steps right there. But the user interface. Now, this is in the design of a robotic system. The way I'm teaching this class, I'm not teaching you how to design robots, but just kind of going over what's inside them. That's there. And as I mentioned the first week, I don't anticipate anybody going through this program to be working for Mitsubishi designing robots. Hopefully I'm wrong and somebody gets a job making 150,000 USD a year, working in Japan, all living expenses paid, designing robots. That, or Mitsubishi opens a big design center here, and they have lots of people designing robots. I've just kind of watched the behavior of Japanese companies, and they don't move much R&D outside Japan. Just like in the U.S., they don't move a lot of real R&D outside the U.S. You tend to keep that intellectual property close to home, which makes it difficult for countries that want to develop that technology because they have to kind of reverse engineer. But that's what Japan did back in the 1950s and 60s. So, and that's what Taiwan has done, and Korea has done in recent years. They've developed that. These are the key components. Again, some version of this I will expect you to know right there. So I'm kind of going over some things that are going to show up on the final exam right there. There may be a slightly different version of this. Keep in mind that when I grade final exams, there is not one right answer in a lot of my questions right there. Okay, here we're talking about the robot base. This is getting a little bit more detail, and that's there. What is this stuff here that pops up in the middle of my lectures? I wish it wouldn't Microsoft quit doing that. Here we're talking two different types of robots with two different types of base systems. The one on the left is a typical industrial robot, right there. So as you look at the robot, it says it's an A255. I have no idea. Its company is CRS Robotics. That's a U.S. company, right there. So, but as we can look at this here, you can see the base is the black part on the bottom. That there, that's fairly clearly the base. We see 1 degree of freedom where the white meets the black, and again I can't draw because we're a projector here, but where the white meets the black, that rotates a number of degrees. I am guessing it's probably 270 degrees, not a full 360. Anytime you start rotating 360 degrees, then you run into the problems of cables twisting. So most robots only rotate 270 degrees or even 300 degrees. We have another degree of freedom where you can see the big, the two things protruding, which I don't know. If I bring this, yeah, you can see where these two are right here. That's another where this robot, this arm can go this way right here. That I have to assume to be some type of motor right there, housing that they're holding, sticking there. We have another degree of freedom up here. Then we have another degree of freedom here. Then we have another where this rotates as well. And then we've got our gripper to grip whatever we want to pick up or set down. So as we look at this one here, 1, 2, 3, 4, 5 degrees of freedom right there, plus the gripper. That's almost identical to the ones that we're going to be working with. It doesn't look like this, but it's pretty much the same degrees of freedom right there. And it's got the same end actuator right there in terms of a gripper right now. So, but this is but it's bound to a base. That's what this slide is trying to get across. I'm getting sidetracked there. And this is a fixed robot, fixed base. This is our little 4-legged or 6-legged insect right there. You can see actually 4 moving legs and one that is fixed. Right there you see the servo motors here, there for moving the legs. This one is actually one that walks. It looks like it's got some camera. It's got a big capacitor, so we have to assume that this one here is actually one built in the lab for research, not, this is not used for any real work. Typically, if I'm going to build something and sell it for industrial use, I wouldn't leave electrolytic capacitor sticking out of the top like that. But if I'm throwing something together in the lab to see if it works, why not? Who cares? So that's a fixed versus a mobile base right there. This is getting a little bit more, and I'm not going to spend a lot of time on these slides right here, but here we're talking about some mechanical mechanisms for that they're, this all is going to vary with the setting right there. If you're driving a transmission or for example, a satellite dish moving across, or you're moving something large, then the rack and pinion right here. This is a rack and pinion. This is a gear and rack. This is a cam and follower. This moves it up and down by rotating. This is actually the way your car engine works right there. As you rotate, shift the up there, only it goes the other way, it pushes the cam down right there. This one here this rotates and moves it up and down. The lever, it just gives you more balanced movement, the chain and sprocket. These are all different mechanical actuator type systems right there. That's not really part of this course. This is more in terms of what you want to move in terms of robot. And keep in mind that if you're actually trying to build a robot for, to do something, you may need and use any of these various types of mechanical tools. but this falls under the area of the mechanical engineering. In robotics, actually, is a blend between electrical, computer, and mechanical engineering. It is, because you are trying to do mechanical work, but you're trying to control it with a computer system. And you have to use electronics as your interface between the computer and mechanical. So all these play into that there. I'm not an expert in any of these. I don't know. When I worked in industries where we've dealt with robotics, the industrial and the mechanical engineer came out and took care of those things. Myself as the computer person, I worried about interfacing the robot to our main computer systems that control industrial, things on the factory floor. That's there. The power engineers took care of getting the power to it. So, we worked in a large team. In my experience, has been just a little slice of some of this stuff, and I don't have a lot of that. I'll be honest, I have not done a lot with terms of industrial robots. I've just been on the edge of it a few times, where we've had, because my job when I was at Magnavox was dealing with data acquisition from the factory floor and doing reporting and doing testing of sonobuoys and things like that. And we had robots that we put out on the floor, and I had to interface to the robots to get information into the robot from the robots for my data collection activities, and for my test engineering, I had to tell the people know where the robot was in a certain position. So I was sat there, and that was 35 years ago. So don't quote me on how. Don't ask me to do it today. I did it way back in the dark ages. So now, this is one area that I am relatively familiar with, and we're going to spend a little bit more time talking about sensors right there. But the human has a number of, right there. The human has a number of senses. We have, typically they say we have 5 senses. That there are many people that say that there's actually more than 5 senses that they're detecting. But the most common one is sight, sound, touch, taste, and smell. Those are our 5 senses that we deal with. There are sensors designed to do all 5. Believe it or not, there are sensors that will actually do taste. There's many sensors that work on the idea of, smell, right there. So, I mean, if you look at detecting a gas, for example, in terms of a natural gas leak in your kitchen, the way that you can sense that when you walk into your kitchen is you smell gas. Now, natural gas is actually odorous. And it wasn't until the 1940s there was a huge explosion at an elementary school in Texas. And it was caused by a gas leak. And the government at the time figured out that if they required gas companies to put something in the gas to make it smell really unique and nasty, that the explosion could have been prevented. And there was like 50, 60 school children killed. There's nothing to motivate, safety requirements than a bunch of school children killed. Now, if it was an old folks home, a bunch of old men like me, nobody would care, but, 4 or 5 year olds out there. So, since they put the smell in, now there's many sensors that are in buildings that will look for that smell right there. So, another area, sensor that you come up with for robotics is, I mentioned, the alcohol sensor. Now, ethanol is a chemical that's there. Most of you know it as alcohol that's consumed by non-Muslims, and unfortunately some Muslims, that's there. you know, and this is not a moral discussion or out there. But one of the effects of ethanol is that when you consume it, your reaction time, your coordination, your logical thinking is greatly impaired out there, depending on how much you consume right there. So most countries, Malaysia being one of them, have passed laws that says you cannot consume ethanol and drive right there. That's just one of those things that there. And as a general rule, at one time in the U.S., alcohol-related deaths were the most common form of accidents, or that there. It's not anymore, actually. Can anyone guess what the #1 cause of car accidents is today? What? No. No, alcohol influence is #2. Cell phone. People distracted driving, people playing with their cell phones has killed more people in the last 3 or 4 years, 5 years, than alcohol has. That's there. And I'm sure that's the #1 cause in Malaysia too, of accidents. So, but regardless, you know, one of the you know, I spent probably a year and a half, probably close to 2 years, very, very tightly involved in being able to sense alcohol for an alcohol interlock system right there. So I'm very familiar with using various sensors, and the way that particular one worked is you breathed into it and it measured the flammability of your breath. Because alcohol is one of those chemicals that actually will burn relatively easily in comparison to water or so if you take a bottle of ethanol, you know, whiskey, vodka, whatever, you can actually light it on fire, right there. So we would measure the alcohol contents of a person's breath by how much heat we had to apply in order to catch their breath on fire. So a lot of engineering in terms of sensing technology, you look for something unique in that chemical, that smell or whatever, and to try to determine what that is. And that's what engineering's about, is you have to figure out a way to sense whether there's natural gas in this room. What is there about that smell that would make it unique that you can electronically sense it right there? And that's what sensors is all about, is you have to be able to sense something that you and I could sense easily. I mean, you can walk up to me and you can start talking to me and I can tell instantly whether or not you had a glass of whiskey before class, because I could smell the smell of the whiskey and the alcohol. You know, I know what that smells like. Now, you may not be able to tell that smell on my breath because you're not familiar with it, but you know, everyone knows what beer smells like. You've walked by places, okay. But you can tell the smell. We've been taught to know the smell of natural gas, right? How do you do that electronically? That's a big challenge that there. So emulating the senses, you know, the sense of sound. Now the sense of sound is a unique one because it's very easy to program robots to hear and to record sounds. It's not so easy to get robots to understand the sounds that they hear. Speech recognition is a huge, huge area that there's been research done on 30-some years on that, and they're still working on it. My capstone course and most of my master's research dealt with the recognition of vowel sounds in human speech, how to pick up the start and the end of a word and determine whether or not the person is pronouncing it right for speech therapy. You know, that's what I saw. Being able to recognize human speech is a very difficult thing to do by robots. That's it. And as we look at those robotic films that we were looking at, you know, people talk to these robots and they expect these robots to understand them. One of the things that I did right after my stroke is that I had some work I was doing, and supposedly I had to do quite a bit of typing. My right hand still doesn't type very well right there, and I still use it. There's a program called Drag and Dictate right there. And Drag and Dictate, and I don't know how well it will work right there, but I installed it on this computer. And where is it? I'm sure it's on here somewhere. Oh, I don't want to know about the weather. Oh, here it is, right on top, because I was using it quite a bit right there. And I actually purchased this while I was in the hospital in order to respond back to emails and things like that there. So, right there. I'm not sure how well it's going to work with recording this and only have an 8 gig of RAM in this computer, but we'll try it. Right there. Initializing. And I can click on this. And at this point, it should pick up my speech and put that in a text box. I probably have, yeah, that's it. And notice that it says Xbox. So it's not real accurate right now because one is this room's fairly noisy, and two, the computer's slow because of the fact I'm recording right there. And I'm doing this with a laptop instead of my, you know, this is one of the reasons I have a bigger computer at home. But as you see, it does work. That there. But it's extremely slow, and let me shut it down. Yeah, we'll just turn off the microphone. Right there. So, again, when we look at, when I talk, typically most people can understand me if they understand English, my accent, and those kind. I know some of you might struggle with that there. Probably wish you had something like Drag and Dictate so you could read instead of trying to pick up mine. But again, you can see the problem though with trying to come up with a program like Drag and Dictate though, is that being able to pick up my speech and picking up your speech with your Malaysian accent is two totally different problems. So again, these are things that when we look at robots and we look at sensors, sensors measure robot configuration, condition, its environment, that's there. Again, they send information to robotic controllers such as electronic signals that they're arm position, presence of toxic gases that they're. Incidentally, does anybody know what was used back 100 years ago to look for toxic gases? What? They'll look for toxic gases, say if you're in a coal mine. How did you know whether or not there was methane gas there? They took a canary, a bird, down in the mine with them, and when the canary passed out, it's time to get your butt out of there, and hopefully you get the canary out before it dies. But the canary was more sensitive than the people, so the canary was sitting there, and as long as that canary was chirping, 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 everybody was happy. Once that canary went quiet, they knew that they hit some gas up there. I think I'm going to kind of wrap up up there. You know, I hate to keep these classes short, but to be honest with you, I can only go so long up there. Monday, Hold on, let me see, let me finish the slide here that they're, okay, they say, here they give an example of the accelerometer. We'll talk about accelerometers. An accelerometer measures how fast you're accelerating. So they're quite often used in vehicles or aircraft and things like that. Braking. A decelerometer is in every automobile because that's what's tied to your airbag. To know if you're deaccelerating at a fast enough rate, the airbag is deployed. That's there. This is a flex cable. It's got actually, we'll talk about this one in more detail, but actually if you look at this, we've got a sensor here and then we've got two long electrical wires in there. As we bend the wires, it causes an electrical voltage that's there. So the last bullet on this is robots often need information that is beyond the 5 human senses. I've already talked about that. The ability to see in the dark, that they're infrared cameras, infrared sights on weapons, that they're, so you look for optical images that they're, where you use infrared or other technologies to see where the human eye can't see. Same thing with hearing. Quite often you will place hearing, sensors, audio sensors that will work beyond the range of the human ear. That's there. Smell. That's there. Again, for example, certain animals can smell better than humans. I mean, dogs are used very, very prevalently in drug detection and hunting for dead bodies, because they can smell things like that better, tracking individuals. So dogs have a very keen sense of smell. So a lot of computer systems emulate that sense of smell. I haven't seen it in Malaysia, but in the U.S., a lot of times, if you go through, into an airport to have your baggage checked for weapons that they've got sensing stations where they'll rub a cloth on it and put it into the sensor to look for explosives. So there's sensors that will sense things that we can't sense, right? So, and a lot of robotics depends on sensors. That's probably 25% of the work done in robotics is sensing. A lot of them right there. So I'm going to kind of let you go. I'm going to, I need to stop the recording. I'll probably that's a short lecture. Well, not really.